What I'd like to do is take some time now to really emphasize the key concepts that we have done through the entire class of calculus. These are major takeaways that if you want to be prepared for future calculus classes, I really hope that you understand these. These are going to make all of the calculus concepts and thinking calculus going to make it come so much easier if you have all of these really pounded into your head. Okay, so the first thing is that limits are a process. Remember, we started out talking about limits. We had this limiting process. Remember, limits are always useful in describing something kind of changing. So this is really important for everything we're going to do in calculus because we saw, for instance, derivatives was this average rate of change, and integrals were also taking this process of change. So limits is a process. Okay. Now derivatives are based on secant lines approximating tangent lines. So we saw this on the first day of class. We found the slopes of secant lines. So the limit of the slopes of secant lines give the exact slope of the tangent line. So it's this process. Remember, we took these secant lines and we started getting closer and closer to the tangent line. This process was this limiting process. So what that looked like when we defined the derivative of a function was this was the limit as h tends to 0 of f of x plus h minus f of x divided by h. And what this is based off of is based off of slope, the slope of the secant line. This is going to be the change in y. So these were the two different y values divided by the change in x. So we saw this, say this was our picture here. This was, say, going to be x. This distance here was going to be x plus h. So this width is h. So this, the change in y over the change in x, we're taking a look at this line here. The change in y is the difference between the y values. That's f of x plus h minus f of x. Change in x is x plus h minus x, which is just h. So this was our definition of a derivative that used limits. Now, definite integration, this was now what we moved on to after derivatives. Definite integration gives us the net area under a curve. So we're going to be doing a lot in Calc 2 of integration. So if we remember that definite integration gives us the net area under a curve. So how we started with this was that we saw rectangles could be used to approximate the area. So if we have weird things, we don't know the area formulas, we can use rectangles to approximate it. But then again, the limit of taking rectangles of infinitesimal width. So we took these to be as skinny as we possibly could. Or in other words, take as infinite number of rectangles that are all equal width. That limiting process gives us the exact area. So a lot of calculus is this process of taking the approximate, limiting it to become the exact. So if you can remember that, here we took an approximation, limited it, it became exact. Here we took an approximation, we limited it, it became exact. So what we saw this limit was we took the sum of all of these areas of f of c sub I times delta x. So we had the height of all of our rectangles times the width of our rectangles. And then this was the sum from I equals 1 to n, and what this ended up giving us was the exact area of f of x dx. So we had this sum here, when we took the limit, became this integral. And this was the limit process, this limit definition of integration. And then the last thing to connect these, because remember, we said at the beginning of this class, there's three major concepts. We have limits, we have derivatives, and we have integrals. All three of these are interconnected. We have the relationship between derivatives and limits, integration and limits, derivatives and integrals. That's all because of the fundamental theorem of calculus. The fundamental theorem of calculus allows us to now relate integrals and derivatives. We have this relationship between the two of these, which, granted, why is there a relationship between slopes of tangent lines and areas underneath a curve? It's still somewhat mind-boggling, but there is, allows us to relate these. And so this is always going to be the way that you integrate from here on out. So anytime we're trying to integrate, you're going to be thinking, what is this antiderivative of the function I'm given? So the integral from a to b of f of x dx, this was going to be this f of x evaluated from a to b, which was going to be f of b minus f of a. So this was our fundamental theorem of calculus that we're going to use all the time. Find this antiderivative of this little f of x, and then we plug in the top number, subtract off the bottom number. So this hopefully maybe helps bridge all of the major concepts. So if you understand all of this, that's great. You're really ready to move on and learn more calculus. But if you don't understand these base concepts, as we start to add on more and more behind calculus ideas, and you don't have a strong foundation, it's just not going to make that much more sense when we're starting to apply this to different concepts that use calculus.